Hi, my name is Tom Lever. This is part 7 of Little YOLO version 4 and how YOLO version 4 darknet and convolutional neural networks work. In this video, I would like to briefly go over darknet's load image color and introduce my own simplified, more intuitive version called imread convert color and create image. Here in Little YOLO version 4, let's take a look at load image color. We are here loading alphabetic character images into a two-dimensional array of alphabetic character images. The method load image color, after it has been simplified, only returns the output of the method load image. Load image returns the output of load image CV. Load image CV takes the file name of, in this case, the alphabetic character image, and the number of channels, being 3, a color image, and loads the alphabetic character image into an Opencv matrix, and then converts the matrix into a custom image object. We will have both of these functionalities in imread convert color and create image. Taking a look at load image mat. Load image mat calls load image CV, which returns a pointer to an allocated and read Opencv matrix. That pointer is then dereferenced into a new matrix, and that matrix is returned. Why not just return the loaded Opencv matrix? Taking a look at this method though, this method again loads an alphabetic character image into an Opencv matrix, then actually converts the matrix from red, green, blue order to blue, green, red order, then allocates new memory in heap for a new version of the Opencv matrix, returns a pointer to that heap memory, returns the pointer, and then that pointer is dereferenced and another Opencv matrix is established. Very convoluted. Going back a few steps, the returned Opencv matrix is then converted to a custom image object, and we first store the width, height, and number of channels properties of the matrix in single character variables for ease of use. And for speeding up this nested for loop, we make an image that consists of a custom image object with null pointer for the pixel data and height, width, and number of channels properties based on the matrix. And then in this parent method, for some reason, the pixel data for this custom image object is allocated in 0 initialized. Then, for ease of use and speed, we store the pointer to the pixel data in the Opencv matrix in a new pointer called data to unsigned bytes, and then iterating over number of channels, the height of the image and the width of the image, we read the appropriate pixel from the Opencv matrix pixel data, scale it down between 0 and 1, convert it to a floating point number, and store it in the appropriate location in our custom image. Then we returned the custom image object representing the alphabetic character. And we continue to return that image object. And then again, it is stored in our two-dimensional array of alphabetic character images. To me, that was very complicated and a lot of methods. So let's work to create our own version of all of that functionality. I call it imread, convert color, and create image, because those are the three principal functions of all of the methods that we just looked at. Okay, so here we are with little YOLO version 4 for viewers. We haven't established load image color over here. Instead, let's establish imread, convert color, and create image. Let's declare it. Over here, I'd like to see if it works before taking a look at how it's structured. So let's switch it out and not use load image color, but use imread, convert color, and create image. Let's give this a build and a run. Okay, things are working, so let's dive into how my custom method works. Let's finish the declaration. It takes a file name. Just a reminder, here is the template for creating a custom image object. It has a width, height, number of channels, properties as integers, and a pointer to a yet to be established memory buffer of 32-bit floating point numbers representing pixels. Okay. Here is our declaration of imread convert color and create image. Let's create the definition. Okay, so how does our custom method work? Well, let's write out the comments first. Then we can go into the specifics. Load image as an Opencv mat object called mat. Format is NHWC. We'll go over what that means. Then convert Opencv matrix mat from RGB order to BGR order. This statement could be eliminated after retraining. The YOLO version 4 .waits file was established based on passing BGR ordered images through the convolutional neural network. We can't simply eliminate this statement at this time, but after we introduced training functionality to little YOLO version 4, we could probably eliminate this statement. We could also probably eliminate this statement in darknet, but you might have to be careful about all of the different methods that might use it. And then we create a custom image object based on the Opencv matrix mat. And let's say here that the format is NCHW. We'll also take a look at what that means. Format is NCHW. Okay, and then finally this method returns the custom image object representing an alphabetic character image, at least at this time. So that's the overall structure of the method. Let's take a look now at what NHWC and NCHW mean. So I'm going to minimize Visual Studio right now and show you a representation of a toy image in blue, green, red order. This is a theoretical geometrical model of a 6 by 6 by 3 image in theoretical blue, green, red order. So when we read a geometrical theoretical image into the pixel data pointed to by the data pointer of Matt, this theoretical object is read into a linear, one-dimensional memory buffer. And here is the buffer in NHWC format. So the imread method basically takes an image file, which could be conceived of as this ideal theoretical geometrical image object, and takes the pixels in this block and arranges them in a memory buffer like this, where every pixel contains a 32-bit floating point number. So let's actually zoom in and kind of, I'll lay out the kind of visual process of converting this theoretical block to this linear memory array. So here we are at the front end at index 0. So the imread method roughly takes this first pixel and puts it in the first location in the NHWC buffer. Then the imread method takes this first green pixel and puts it in the second memory location. And then imread takes the first red pixel and puts it in the third memory location. Proceeding from there, this triplet is put here in the second triplet location. This channel is put here, and so forth. And when we finish up with this pixel, we jump to the next row and take that triplet and append to the tail end, wherever we are, in this long memory buffer. Then we take this channel, starting with the second pixel in the second row, and then we work with the green and the red. Then we take this pixel, then green and red, then this one, and green and red. So that's the conversion of a blue, green, red geometrical image object into an NHWC memory buffer. So what are those letters really saying? Well, on the right of the NHWC is the C. So that means when we start in the upper left hand corner of our image object, we then move along the channel's direction when linearizing this object into a one-dimensional memory buffer. And then once we're done in this channel's direction, we move to the next location in the width direction, which is the W. And then we go in the channel's direction again, adding or filling in our 1D memory buffer. And then once we're done with the second position along the width, we go to the third position along the width, and then follow the channel's direction again. And once we get through all of the width direction in the first row, then we jump to the next pixel in the geometrical object, which is in the second row, and rows are in the height direction or the H direction. And then we follow channels again, and then width again. And then once we're done with this red pixel, we go to the third row in the height direction. Then we fill along channels, and then fill along width, and then jump again in the height direction. So that's the H, the W, and the C. What's the N? Well, if you were passing a memory buffer like this that was 4 times as long, because it represented 4 images in a subdivision with the advantages of preparing to use batch normalization, then this might be your first geometrical image object that you are entering into a really long memory buffer, and then you might have another image object just like this, like over here, and you'd follow that same HWC process, and N is representing what image block you're on. So once you finish entering all of the pixels of this geometrical image object, this first object, then you start working channel-wise, then width-wise, then height-wise on your second image object. Once you finish with the second image object, you move to the third, and then you move to the fourth. And so you're moving first in channels order, then in width order, then in height order, and then you're moving in image block order. And ultimately, if you had 4 6x6x3 images, then you'd have a 1D memory buffer of 4 images, so n equals 4, 6. So the number of elements in the memory buffer would be 4, n equals 4, times h equals 6, times w equals 6, times c equals 3. So that's the gist of NHWC format for a theoretical image object. Taking a look now at NCHW, I'm going to minimize this depiction of the NHWC memory buffer. And what do we have here? We have a representation of the NCHW memory buffer. So here, instead of taking this first pixel and putting it in the first location in our buffer, and then taking the first green pixel and putting it in the second location, and then taking the third pixel, the first red pixel, and putting it in the third location. Now we're going to take this first blue pixel, put it in the first location, move across the width first, take this second element of this blue channel, put it in the second memory location, take the third, put it in the third, and so forth across this width. Then once we're done moving across the width of this blue channel, we go to the second row, first pixel in this blue channel, and we continue adding all of these into this blue section of this one-dimensional buffer. And the length of this solid blue section of this 1D memory buffer is the length, or is the number of pixels in this channel in this geometrical representation of an image object. Once we're done with all of the blue pixels, we move to the green pixels, following first width, then height. And then once we're done with all the green pixels, we move in the channels direction again to add all of the red pixels into the red section. So first we moved in the W direction, then we moved in the H direction, then we moved in the C direction. And if there were multiple images that we were adding into an input tensor to utilize batch norm, say one here, one here, one here, and one here, this 1D memory array would be 4 times as long, and we'd move after entering all of the pixels in the first image object onto the second image object, then onto the third, then onto the fourth. That represents the end there. So these two depictions are the NCHW memory format. Okay, now we can return to Visual Studio and continue to figure out how imread, convert color, and create image actually works. So to load an image from a file as an Opencv matrix object called nat in RAM, presumably, in stack RAM, I mean, let's declare the object, and this requires including opencv2 /opencv.c++ header file, and then we define this matrix object as the output of Opencv's Immorate method. We pass it a file name, which in this case is an alphabetic character image path, and we pass it a flag indicating that we're reading in a color image into a color matrix. Again, this line is required to use YOLO version 4.waits. It may not be necessary after retraining little YOLO version 4. We're converting the Opencv matrix that we loaded from RGB color order to BGR color order. Then let's allocate memory for a custom image object. that will be in NCHW format for the rest of this convolutional neural network functionality. And then we fully create this image object by calling the createImage method and passing createImage the address of the image object we just allocated and the address of the Opencv matrix object that we loaded. And then once image im is fully created, we return it, and it is stored in the two-dimensional array of alphabetic character images. Now let's take a look at createImage. First we declare it. Already exists. Okay. Well, this is the second time I've recorded this video, but let's get rid of it and start fresh. CreateImage, declaration. This is a void method. It returns nothing. It's called createImage, and it takes in a pointer to an image object, and the pointer is called im now for this method, and it takes in a pointer to a matrix object, the pointer or the address to CV matrix mat. This needs to be a capital M here. Okay, that's the declaration for createImage. Close that out. No return. CreateImage takes in a pointer to an image object and a pointer to an Opencv matrix object. Great. Let's take a look at how createImage actually works. Okay, so first, let's define integers w, h, and c as the width, height, and number of channels in the Opencv matrix object called mat. No. Pointed to by mat. And let's also define pointer data as the pointer to the pixel data in the matrix object pointed to by mat. Pixel data in the matrix object pointed to by mat is unsigned byte pixel data. Okay, then based on the width, height, and number of channels in the Opencv mat object pointed to by the address of the mat object that we loaded, let's define the width, height, and number of channels and data properties of our new image object. So for the pixel data of our image object, we are allocating enough space for width by height by number of channels, floating point numbers between 0 and 1. The next section of the create image method is the hardest. Let me write out the comment first. For each channel in image object im, so for each channel here, while given a channel, for each row in im, so let's say for each row in the blue channel, and then while in each row for each column in im, define the present pixel in the memory buffer pointed to by im's data pointer as the corresponding pixel in the memory buffer pointed to by mat's data pointer. The present pixel that will be read from the memory buffer pointed to by mat's data pointer will be scaled to between 0 and 1 and converted from an unsigned byte to a 32-bit floating point number. That's a lot. So what's going on here? Well, basically, we're iterating over all of the pixels in an image object, either the geometrical representation or the custom image object with an NCHW format, or we could be iterating over the mat object with its NHWC format. But I think it's most useful to iterate over something we can imagine. So let's specify the parameters for every cell in a geometrical theoretical representation of the alphabetic character image. And then once we have the parameters for a given cell in this representation, we can find the corresponding pixel in image object M, and we can find the corresponding pixel in matrix mat. So how do we specify all of these parameters? Well, let's do it with a nested for loop. So let's let's iterate as if, let's iterate over this image representation as if it were in NCHW format, so in the format of the final image object that we're creating. So that would involve stepping first over the cells in each row, and then once we step through the cells in each row, we jump rows and walk through the cells in that row, jump rows again. So after iterating across a row, we iterate down through the rows in a channel, and then we iterate across the channels in an image. Okay, so this statement iterates us across a row. This statement changes the row that we're in, and this statement changes the channel that we're in. Okay, so given the column index, the row index, and the channel index in a geometrical image representation, we have the three-dimensional parameters for one cell in this geometrical image. So now the question is, given the parameters for one of these cells, what is the index for where one of these cells should be put in this NCHW one-dimensional memory buffer. So let's create an Excel workbook for this. Our three-dimensional geometrical image parameters. So parameters for each cell in geometric image are x, the column index, y, the row index, and k, the channel index. And we're iterating as if we're following NCHW format. So let's start by going across the cells in one row, and then we'll go down following the rows, and then we'll go back following the channels. So there, in our toy image, there are 5 cells in a row, and the first row has index 0, and the first row also has channel index 0. And then the second row has column indices 1 through 5, row index 1, and channel index 0. And then the third row has row index 2 and channel index 0. And the cells in that third row have column indices 0 through 5 as well. So there's a bit of a pattern. Then let's skip a whole bunch. And what are the three-dimensional geometrical parameters of the pixels in this first row of the green channel? Well, within the row that they're in, they have column indices 0 through 5. The first row in the green channel has a row index of 0. And the green channel is the second channel, so it has an index of 1. And then the second row has column indices 1 through 5. And we're in row with index 1 in the green channel, and the channel index for the green channel is 1. Let's skip again. And what are the indices, or what are the parameters for the pixels in the first row of the red channel? Well, the column indices are 1 through 5. The row index is 0 again, and the channel index is 2 because it's the third channel. And then the next elements have column indices 1 through 5 again, but now we're in the row with index 1 in the red channel, and the channel index itself is 2. Let's skip a bunch, and then what are the indices of the pixels in the last row of the red channel? Well, the column indices again are still 1 through 5. The row index is 5, and the channel index here is 2. Okay. So let's also here include global image parameters. So those parameters are the width of the image, the height of the image, and the number of channels in the image. And these are always 6, 6, and 3. All right. Now, we've basically laid out lots of combinations of parameters for various cells in this geometrical image representation. And these are also our for loop indices so that we can make sure to cover every pixel. So given a pixel code, I guess, in this geometrical representation, what is the corresponding index in this one-dimensional NCHW memory buffer, which is basically how an image is represented in our new image object? Well, this 0, 0, 0 pixel over here goes into location 1, or into location with index 0. This 1, 0, 0 pixel goes into the first location. This 2, 0, 0 pixel goes into the third location. This 0, 1, 0 pixel goes into the 7th location with index 6. So let's just write some of that out. Index in 1D N CHW buffer. So the first 5 elements here in the top of the blue channel have linear indices 0 through 5. And then the first element of the second row has 6, and the second element in the second row has 7. And then it just increases linearly because we're in a linear memory buffer. Okay, but then we skip a bunch. And now we're in the green channel. So what is the index of this first cell in the green channel? Well, it's the number of elements in the blue section of the memory buffer plus 0 for the index of the first element in the green buffer. And what is the number of pixels in the blue channel? Well, it's the width of the blue channel times the height of the blue channel. So the first pixel at location 0, 0, 1 is the index over here is 0 plus 36 or 36. And then the next element over here, which is in the first channel, first row, green channel, first row, second element, has the next linear location, and so forth. Okay, now we're on to the red channel. Well, what is the index of the 0th element of the red channel? Well, it's the number of elements in the green channel plus the number of elements in the blue channel, or 36 plus 36, or 72. And again, the first element in the 0th row in the red channel is the next in the linear array. Then, what are the linear indices of the pixels in the last row of the red channel of this geometrical image? Well, it's the number of elements in the blue channel plus the number of elements in the green channel plus the number of elements in the first 5 rows of the red channel, which is 6 times 5, or 30. So 36 plus 36 is 72, plus 30 is 102. Okay, and what's 36 plus 36 plus 36 for, the total number of elements in either this buffer or the geometrical image? It's 108. So here we have a mapping between the parameters for a pixel in this geometrical image and the corresponding location in this NCHW buffer. Okay, so what's a formula for this mapping? It's a one-to-one function. Well, I'm just going to give it to you. This is x plus y times the width plus k times the height times the width. Let's fill that in. It looks like our function that we chose was correct. Okay. So now, what is the corresponding index in a one-dimensional NHWC buffer? So what is the mapping between pixel parameters for this geometrical image and the corresponding location in this one-dimensional memory buffer? Well, the parameters of this pixel are 0, 0, 0, and this first pixel becomes the first element of this array. So we put a 0 here. 0, 0, 0 maps to 0. And then this green cell, since now we're in NHWC format, goes to the second location in this NHWC buffer. And the coordinates of this green pixel are 0, 0, 1. So where is that here? Oh, it's over here. So the index of the linear location of the pixel with parameter 0, 0, 1 in this block is 1. And then the pixel, this red pixel has parameters 0, 0, 2, and this pixel goes to the third location with index 2. So where's that? It's here, 0, 0, 2. Okay, and then let's go back to this block. And what's this pixel? Well, it has parameters 1, 0, 0, and it has location with index 3. So 1, 0, 0 is here, and it has linear index 3. And then this green pixel has index 1, 0, 1, and it maps to linear index 4. So where's 1, 0, 1? Well, it's here. Beginning to see the pattern? The pattern turns out to be this. Okay, I'm going to leave off there. So each pixel in this geometrical image has a unique location in this NHWC buffer. So there's a functional mapping between the parameters of one of these pixels over here and the linear location in this NCHW buffer. What's the mapping? Well, I'll give this to you as well. It is the channel index plus the row index times the number of channels plus, oh sorry, this is column index, excuse me, plus the row index times the width of the image times the height of the image. Let's bring this all the way down. These look right. These look right. And these look right. So I'm just going to say these two formulas are correct. Okay, so now making this relevant to little YOLO version 4 for viewers, define the present pixel in the memory buffer pointed to by im's data pointer as the corresponding pixel in the memory buffer pointed to by Matt's data pointer, scaled to between 0 and 1 and converted from a byte to a 32-bit floating point number. So these for loops specify our parameters, and then what is the present pixel in the memory buffer pointed to by im's data pointer? Well, the present pixel, given these three geometrical parameters, is im.data, and you saw this formula before, x plus y times w plus k times h times w. And given these parameters, what's the corresponding pixel in the memory buffer pointed to by Matt's data pointer? Well, it's the data pointer here. And we need the mapping formula for the NHWC buffer. This is K times X times C. Sorry, K plus X times C plus Y times W times C. So given parameters that we're iterating over to take care of every element in this geometrical model, we found the present pixel in the new image that we're creating in NCHW format, and we found the present pixel in the mat object that Opencv loaded for us. So now our objective is to read this data pointer, scale it to between 0 and 1, and convert it to a 32-bit floating point number, and then to write it into our new image. So that takes care of mapping the Opencv matrix into our new custom image object. I'm just going to quick check these terms, x plus y times w plus k times w times h, and k plus x times c plus y times w times c, all over 255. Looks good to me. So I think we're done with creating an image based on an Opencv matrix and filling in a new custom image object. So let's close out create image. Here, this is another time that I've recorded this video, but I think the last time you saw it, we had it like this, so we need to include create image. And now we're done with imread, convert color, and create image for alphabetical character images. And then here we are in load alphabet, and we include imread, convert color, and create image, and that takes a file name and fills in a two-dimensional array of alphabetical character images. That completes load alphabet. We come back to test detector, and now we have a pointer to an array of pointers to alphabetic character image sequences. Now that we have load alphabet complete, let's do a little cleanup and let's test that our two-dimensional array of alphabetic character images actually contains images that we can convert back to matrix and display using Opencv. So over here in little YOLO version 4, I'm going to exit out of create image. And then here in imread convert color and create image, this is complete and clean. Load alphabet. I can get rid of references to load image color now that I have my own custom method. And I'll close out of load alphabet. And now I'm back to test detector. So, how can we test that this two-dimensional array of alphabetic character images is correct? Well, I have some code for you. First, this relies on a method called imread, which is the reciprocal of mat2image. So we're only using it for testing, so I'll put it over here in little YOLO version 4 for viewers, but I think once we're done, I'll exclude it from the building process. It may come in handy later. Let's take a look. I've cleaned it up relative to darknet, so hopefully it looks familiar. Over here in little YOLO version 4 for viewers, let's create the declaration. It takes in a custom image object and outputs the matrix version of it. Now we define this method. Okay, so we have an input image that we're converting into a matrix. First, let's extract the number of channels, the width, and the height of our image object. Now, based on the image properties, let's create a matrix object with 8-bit unsigned character values with a number of channels of C, which is the number of channels in our image object, which is 3. Okay, you've seen this iterator before. In this case, let's iterate over a geometrical image representation, but as if we were in NHWC mode. So we're going first by the cells, the channels, and then we're going across the rows, and then we're going down in row number. So iterating over the pixels in geometrical image representation as if we were in NHWC mode. Okay, so what is the corresponding value in an NHWC matrix? Well, you've seen this before. The corresponding pixel is mat.data of k times x times number of channels plus y times width of image times number of channels. And given our present parameters in the geometrical representation, what is the corresponding pixel in our input image object? It is image.data of x, since now we're in NCHW mode, plus y times width plus the channel index times h times w. And in this case, we are reading from the input image a 32-bit floating point number between 0 and 1. Opencv mat requires 8-bit unsigned characters between 0 and 255. So first, let's get our floating point number up to the scale of 0 to 255. And then let's convert it to an unsigned character. And then let's set it as, let's set the upscaled pixel value to let's make this value in the matrix that we're going to output corresponding to the present geometrical parameters. Let's set this pixel equal to the upscaled unsigned byte version of the pixel corresponding to these parameters from our input image object. And then we return this matrix that we've just created. So that's image to mat. Exiting out of that on both sides. Now we can use image to mat to display a bunch of our images in this two-dimensional array of alphabetic character images to know that these images are correct and displayable. So let me loosen up some inclusions and some code for testing. So I'm actually going to start with the largest characters because they're easiest to see. So let's use a decremental for loop. For the largest size of alphabetic character images down to the smallest size, find the pointer to the alphabetic sequences of, find the pointer to the alphabetic sequence of images of that largest size. And then, with each sequence, go from character with index 32, so the white space, to character 126, which is the tilde, and based on this pointer to an alphabetic sequence and the index in the sequence, extract the alphabetic character as an image object, and then convert it into a matrix using image to mat. And then let's create an Opencv named window object, which has a string name that can be called to display the object in the window. And this is a normal window. Then show in named window for displaying alphabetic character the alphabetic character, which is a matrix. And wait until a key is pressed so we can take a look at what is actually displayed. Okay. So there's your testing for alphabet. Before running this, let's just check a few things. In properties, make sure that you have references to Opencv, build include, and build lib. And going further down, make sure you have Opencv world 430d.lib if you're running in debug, and Opencv world 430.lib if you're running in release mode. I believe that's all of the Opencv references in the project properties. Also, in little YOLO version 4 for viewers in the data folder. Make sure you have the labels folder with all of the labels in it. Okay. And another thing you might want to check is that this is 127 here, and also in load alphabet you're going from character 32 to character 126. Okay. Those are a few debugging snafus to check over. I feel confident enough to give this a shot. Let's do it. Okay. So this is the largest set of images. That was the white space character we just saw. Exclamation point, double quote, pound sign, dollar sign. So everything looks okay. I'm going to hold down the spacebar and go really fast. Haven't seen any tilde yet. Oh, some braces. There's the tilde. Now we're in white space, and now we're in a little hazier and smaller characters. And it gets hazier and hazier the smaller we go. But all the characters are there and I'm not running into any errors. So we ran through them all. Great. So that's this check that you can do. At this point, I'm going to release this check from little YOLO version 4 for viewers and say load alphabet is finally done. We'll get rid of these inclusions for testing alphabet as well. And let's do some other work for a little bit. So first thing is that later on in test detector, we're loading dog.jpg passed as a command line argument, resizing it using a custom resize method, and then passing in the data pointer associated with that dog.jpg image object into our network bounding box prediction algorithm, which takes the network that's generated by parsing YOLO version 4.cfg. So here, because this goes down into the weeds again with those methods that call each other very quickly and have unnecessary pointers and recreation of images, and also because this resize image method is fairly complex, let's just make our own again. In this case, it's imread resize, convert color, and create image. Alright, so I'm going to comment out Redman et al.'s code. Bring in imread resize, convert color, and create image, which is down here but not included yet. So let's get rid of load image and resize up here and include image resize, convert color, and create image. And also we don't need free image sized anymore because we're not creating image size. We're just creating image m. I want to check that this works before introducing it to you. Okay, it seems to work. So let's take a look at this method. Alright, it should look very familiar to you. We're loading the image as this Opencv mat object in NHWC format. Then we resize to the width and height that's passed to it, which is actually the network width and the network height. And we'll talk about what a network object is and what the properties are later. But right now we're only discussing imread, resize, convert, color, and create image. Okay. And then after resizing our mat object using Opencv, we convert from red, green, blue order to blue, green, red order. And then we create our custom image object based on the matrix mat and return the created image. So I guess the point of this resize is to make the input image square, which makes convolution so much easier. And also to resize maybe a large image down to something that is more manageable for our 11 gigabytes of GPU global RAM. So this method is more or less the same as imread, convert, color, and create image with the addition of the resize. So let's go ahead and create this. We will use this method later. Imread, resize, convert color, and create image. This is our declaration. Takes in a file name to imread. It takes in a width to resize to, and it takes in a height to resize to. And let's define imread, resize, convert, color, and create image now. Then let's load image as an Opencv mat object called mat. Format is NHWC. Then let's resize mat to width by height by 3, because we loaded in a color image. We're using bilingual linear interpolation and resizing to absolute width and height, not scaling. As is required for using YOLO version 4 weights, let's convert mat from red, green, blue order to blue, green, red order. If we develop training functionality for little YOLO version 4, we might not need this command. Then let's create a custom image object based on that. Declare an image object, and then fill it up. And we return a created image. For use by our network predict method. That takes care of imread, resize, convert color, and create image. And here it's in use. Let's try using it in our method. So first I want to check project properties. For the command line arguments, we have data dog.jpg as a command line argument. So let's make sure that dog.jpg is there. It is not yet. So I'm going to go into my main little YOLO version 4 and grab dog.jpg. Paste it in our data folder, and it's dog with a lowercase d. So let me change that command line argument to lowercase d. So that it didn't quite do what I asked. Weird. Did it do what I asked yet? No. Now it worked. Weird. Okay. Now let's read in dog.jpg, resize it, convert it color-wise, and create a custom image out of it, passing in the file name that came from main, and then run detector, and now test detector. And we need to include it. Okay. We don't have network defined yet, so let's just hard code this to 608 and 608, which is specified in YOLO version 4.cfg as the input tensor width and height. And finally, let's test that this method is working by writing some code for testing this image. So suggested code is CV mat, image mat equals image to mat of mat. No, sorry, im. And this is for testing im, I guess. We need to include Opencv 2, opencv.hpp, and include image to mat. Now we want to create a named window for ourselves. Named window for displaying M. And this is a normal window. And then we want to display in our named window for displaying M in as mat. And we want to be able to see it as long as we wish. Okay. I think that's all we need to test imread, resize, convert color, and create image. So I'm going to give it a shot. Well, that's interesting. We have a blue, green, red version of dog.jpg, but it is 608 by 608. So I think that we just didn't include the mirroring conversion back to RGB order. Groovy. But I think this method is working as it should. So I'm going to copy this code over to the little YOLOv version 4 main for safekeeping. I think I'll also mention that this is useful for testing alphabet or in, I suppose. We'll get rid of it here. I like a good clean solution. And just so we don't forget later, I'm going to bring this back to the network width and height parameters for the input tensor to the network. And I can't use that command right now, so I'm going to comment it out we'll use it later. I believe that either Draw Detections version 3 or Show Image is going to use image to mat. I don't know if I'm going to use it. We'll see, depending on all of those really deep dives in the sub-methods that are really more complicated than they need to be. So I'm just going to exclude this from the build for now. Exclude image to mat. I know I'll be reading that, be using that in this line once we have our network established. So I'll leave that in the build. Okay, and here I can minimize this, comment these guys out. And I can get rid of load image and resize image, because now we're using imread, resize, convert color, and create image. I can get rid of Redmond et al.'s lines regarding loading and resizing the image. IntelliSense is freaking out for some reason, but it got better. I'll get rid of free image size because size is no longer created. I like simplicity. Okay. Test detector completely fits within view now on my screen. Awesome. Okay. So also comment that out for now. Let's just make sure things are working. They are. Let's make sure things are working over here. They are. One more cleanup I'd like to do is to get rid of the methods that I replaced. So I believe that starts with load image. I will exclude this from the build, exclude this from the build, exclude. So we are excluding load image and load image color. We're excluding load image CV. We're excluding load image mat. We're excluding load image mat CV. Okay. And then I believe I can get rid of let's just try that. So far so good. Then we can comment out mat2 image. So there's a lot of image processing methods we don't need. I'm just going to scan my list of methods to see if there's any others I might have missed. Activation we haven't gotten to. Add biases. Add pixel? I don't know, this could be a little dangerous. Before commenting that out, again, just make sure that things are working. Yes. I'm going to try this. See if there's any build errors. I believe add pixel was used by resize. Yeah, it's used elsewhere. What's it used by? It's used by, well, resize image. Let's see if we can comment out resize image. Try that. Still a build error. Draw detections version 3 is using, resize image. How interesting. Well, we'll get to draw detections version 3, but let's put these, the add pixel method and the resize image method, back. We'll see how draw detections version 3 uses resize image. Reset things. Life is good. Okay, let's keep going. Border image, that sounds like something draw detections would use. Composite image, I think that might be used for stringing alphabetic characters together. Copy image, what's this used for? Take a look. Let's look at the call hierarchy. Doesn't seem to be used. Or at least Visual Studio couldn't find it. I think it's used. But let's comment it out and see if we can get away with it. Nope. So it is used, but Visual Studio couldn't find it. Create image I used, or I made a bunch of CUDA methods, CUDA methods. Drawing related methods. Image we definitely need. Image to matte. Yeah, we need it for now. What about make empty image? Let's try to exclude this one. What's it used by? A get labels method. Make image. Let's just keep it with us. Can get rid of make image. We'll see. Nope, we need it. That is used by border image. Set pixel is used by resize image, which is used by draw detections version 3. Show image, we definitely need. So there's a lot of image related methods here, but we got rid of a few for sure in this stack. Okay. So again, in this method in this video, we finished up with the image loading functionality for load alphabet, and we also introduced substituting imread, resize, convert color, and create image for load image and resize image in test detector. But resize image is also used elsewhere, so we can't get rid of it yet. But we don't need it in Little YOLO version 4 for viewers yet either. Okay, thanks for watching.